This video presentation is brought to you by the Pro Mathematics Academy.
Welcome back to another video presentation brought to you by the Pro Mathematics Academy. In this video, we'll be looking at the limit of a sequence. And before we can talk about the limit of a sequence, we have to first define what a sequence is. So in simple terms, we want to think about a sequence as either a function defined over the set of natural numbers, or we can also think about a sequence as an ordered set of points indexed by the set of natural numbers S of n. Or we can write out the terms somewhat individually as S1, S2, S3, all the way up to some stopping point, but the sequence usually continues on to infinity. So here we're looking at infinite sequences, of course. Sometimes we use the notation U sub n or A sub n. So in plain language, we want to think about the limit of a sequence, right, as the value that f of n approaches as n tends to infinity, right? And in mathematical notation, we can write that as the limit as n approaches infinity of f of n equals to L. But this is still a simple mathematical notation. We can express this definition more explicitly as for each epsilon greater than 0, there exists a value n such that if we take any n that is greater than this capital N, then we should be within epsilon of L, right? We should be within epsilon of L. That is the same as saying f of n minus n. That is the same as saying the modulus of f of n minus L is less than epsilon. Okay, so note that when we say the modulus of f of n minus L is less than epsilon, it is the same as saying f of n minus L is in between negative epsilon and positive epsilon, which we can write this as f of n is in between L minus epsilon and L plus epsilon. Thus, we say that f of n is within epsilon of L. All right, now let's look at a graphical understanding that can help us to further get insights into what we mean by the limit of a sequence. All right, so let's look at figure 1, right? And if we look at figure 1, what we notice is that we have this these series, or rather sequence of points, that here we're trying to denote the sequence graphically as these points that are curving upwards. But I am able to show you that if we can put in this line right here, then what you'll notice is that our sequence is tending towards L in that form. Okay, so we have a converging sequence, and we say that here we're converging towards L from below. Notice that on our x-axis, well, in this case, our n-axis, each element is a natural number that is being mapped onto the sequence. Okay, let's take a look at figure number 2. Right, and for figure number 2, we see that we have a similar graph, but here we are converging towards L from above. So here, this is L, and we're converging downwards towards L in figure 2. So these two graphs are both converging sequences, right? And let's look at figure 3. We have about 6 figures here. So here we also have another converging sequence, but notice that this time our sequence is an alternating but converging. So it's oscillating but converging as well. And that doesn't mean that every alternating sequence converges, or every alternating sequence converges, okay? Because as we will see with figure number 4, right, we have an example of a oscillating sequence, but this one does not converge to anything, all right? Let's look at another example of something that doesn't converge. Figure number 5, we see that this sequence is unbounded and it's going off to infinity. Figure number 6, we have an alternating sequence, right, that does not converge either. So these 6 figures are 6 examples of the types of sequences that you guys need to be able to recognize in their functional form as well as in their graphical form. All right, so let's jump right into an example of how we can prove that the limit of a sequence is a particular value. So here, example number 1, right? It says, show using an N-epsilon proof that the limit as n approaches infinity of 1 over n is equal to 0. Here, we should recognize that L is 0, okay? So the first thing we want to do when we're doing these proofs is that we want to always remember our scrap work. All right, when we talk about scrap work, we're basically trying to find a lower bound for n. That is, we want to find the inequality n greater than something. All right, and once we find that something, we're going to choose capital N to be equal to that. All right, moving right along. So the first step in our scrap work is always to take that last part of the definition, which says f of n minus L modulus is less than epsilon. Okay, so we're always trying to take that last step in the definition. We always start with that in our scrap work, and then we move on to insert whatever function we're given in the question. In this case, f of n is equal to 1 over n. So here we're going to take the modulus of 1 over n minus 0, which is L, is less than epsilon, which then allows us to say that the modulus of 1 over n which then allows us to say that the modulus of 1 over n is less than epsilon, because we're taking away 0, so it doesn't affect the term. So then we can say that 1 over n is less than epsilon. Since n is greater than 0, 1 over n is also greater than 0. That allows us to remove the modulus without any complications. So then we can say that n is greater than 1 over epsilon. And once we have this, we notice that it is now in the form that we're looking for. What form were we looking for? N greater than something. So now this is saying n is greater than 1 over epsilon. So we're at the end of our scrap work, right? Now let's jump right into our proof. So once we find n greater than something, then we can move right into our proof, okay? And the purpose of the scrap work is not only to find this lower bound for n, it is also to provide a reverse process that we can use when we are doing our proof. So let's start off by saying let epsilon greater than 0 be given, right? Choose capital N to be equal to 1 over epsilon. Notice that here, the 1 over epsilon is the same reciprocal of epsilon that I just found in my scrap work. All right. Then I will say now, n, which is small n, greater than big N implies that n is greater than 1 over epsilon, right? The next step is to basically rework our problem to show that we will be within epsilon of reciprocal of n, which is the first thing that we started out with in our scrap work. So now 1 over n is less than epsilon. I add my modulus, and now I say that the modulus of 1 over n minus 0 is less than epsilon. And believe it or not, we have pretty much completed our proof. So now we can say that f of n minus L, now we can say that the modulus of f of n minus L is less than epsilon, which is what we wanted to prove. So therefore, just to summarize, in summary, if n is greater than reciprocal of epsilon, then 1 over n minus 0 is less than epsilon. Well, the modulus of 1 over n minus 0 is less than epsilon. Thus, we can conclude that this was quite easily done. So that might not be a very straightforward example. So we have a second example here, which says that show using N-epsilon proof that the limit as n approaches infinity of 1 over 3 raised to the power n is equal to 0. Now here, 0 is still our limit, which I chose these simple examples just so we can get used to the process of the scrap work and also summarizing. So we'll jump right into our scrap work as per usual. And as we saw in the previous example, right, whenever we are using our scrap work, whenever we're doing our scrap work, we want to first begin with the modulus of, f of n minus L less than epsilon implies that 1 over 3 raised to the power n, take away L, in this case L is 0, is less than epsilon. We always start with this step, and then we manipulate this expression so that we can get n is greater than something. So let's go. So our next step would mean that 1 over 3 power n is less than epsilon, which means that we can remove the modulus now because we know that the expression is positive. We know that the expression is positive. So removing the modulus gives us 1 over 3 power n is less than epsilon. Now I'm going to transpose for n, right? So this means 3 power n is greater than reciprocal of epsilon. Thus, we can now take the log of both sides, right? We can take the log of both sides, which means that ln of 3 raised to the power n is greater than ln of reciprocal of epsilon. Now, notice that epsilon cannot be equal to 0 and epsilon cannot be equal to 1 either, okay? Because if we have ln of 1, that would be 0. Okay, that was nonsense. Remove that part. Notice we move on to now say that n times ln of 3 is greater than ln of reciprocal of epsilon, which means that n is greater than ln of the reciprocal of epsilon over ln of 3. And now once we have that, we have found our capital N, and we can conclude that we are at the end of our scrap work. So after completing our scrap work, we can always do our proof. And here I'm going to do the proof alongside the scrap work so that we can see that the essence of the proof is coming straight from the scrap work. So now, proof, we say n greater than cap n implies that whatever the cap n is that we just found, we'll take that and insert it. So here we take n greater than ln of reciprocal of epsilon over ln of 3, which now means that I can move on to remanipulate this expression into what we started off with. So I'm going to take n and I'm going to multiply this by ln of 3, and I'm going to say that is greater than ln of 1 over epsilon. Now the scrap work, it is important to keep in mind that the scrap work is not the proof, but the scrap work is the process by which we have obtained our n. The proof is separate and apart from the scrap work. All right, so the scrap work doesn't need to be graded or anything, but we oftentimes think about the proof as the proportion of the question that we are actually grading. Okay, so now continuing with our proof, we have ln of 3 raised to the power n is greater than ln of 1 over epsilon. We can remove the ln from both sides. So this then gives us 3 to the power n is greater than the reciprocal of epsilon, which means that we can say that 1 over 3 to the power n is less than epsilon. We now add on our modulus, which means the modulus of the reciprocal of 3 power n is then less than epsilon. So this means that 1 over 3 power n take away 0 in modulus is less than epsilon, and we have completed our proof. So in summary, n greater than ln of reciprocal of epsilon over ln of 3 implies that 1 over 3 power n minus 0 is less than epsilon. Thus, the limit as n approaches infinity of 1 over 3 power n is equal to 0, right? And I know these examples are still a little bit simple. So we're going to go into one more example that is a bit more tedious, right? And we'll bring out some of these concepts better. So for this example, we have example number 3, right?
That is it for this video. Please remember to hit the notification bell, like, share, and subscribe for future post notification.